Hello guys, and welcome back to this channel. Okay, so in today's class I'm taking guys AC circuit in physics. So this is an important aspect of physics. Okay, and now we advise you to stay to the end of this class. Okay, now this class, these are the outline of the class. Okay, at first you start with the introduction to AC circuit, then move further to the terms used in AC circuit and so on. Okay, now let's start with the very first part, which is the introduction to AC circuit. Now the word AC means alternating current. Okay, it means alternating current. Therefore, the full word is known as what? An alternating current circuit. Okay, so in short form is called what? AC circuit. All right, now in physics we have a different circuit. Okay, we have a circuit that has a direct current. That circuit is known as a direct current circuit. Okay, then the other circuit that carries alternating current is known as what? Is known as an alternating current circuit. In short form, an AC circuit. Okay, so what is an AC circuit? It's very easy. An AC circuit is a circuit with a current and voltage that changes with time. From the word alternating. Okay, so what is an AC circuit? A circuit with a current and voltage that do what? That changes with time, or you can say that reverses with time, or that varies with time. There are circuits that contains current and voltage that changes with time. So that is the meaning of an AC circuit. A circuit with a current or a voltage that reverses with time, or that changes with time, or that varies with time. The current is alternating, the current is changing. Same goes for the voltage. Okay, now let's move to the next part, which is the term used in AC circuit. What are the terms you likely see in AC circuit? Okay, the terms we are going to use in AC circuit. The very first term is cycle. Okay, so cycle. Okay, so now from the word cycle, that is 360, right? Yes. So a cycle is made up of a positive half and a negative half. Okay, I will explain. All right. So in an AC circuit, the current and the voltage. If you look at the board, you see. Don't worry, we'll get to this part. Okay, the current and the voltage are what they are changing with time. Okay. So the first term we're going to use is the first term we are dealing with now is cycle. Okay, cycle, that is, we know cycle, right? 360, right? A cycle is made up of a positive half and negative half. Okay, that we call crest and trough. All right, so now let's say, for example, let's say this waveform. Now, because I'm going to deal, we will deal with this in this aspect of studies. Okay, so a cycle is made up of a positive half, then a negative half. Okay, positive half from this origin above, right? From here, if you go upward, this is positive, right? Yes, if you go up y-axis, that is positive. Then if we go below this origin downwards, the negative y-axis, that is negative, right? Yes. So a cycle, which is 360, is made up of a positive half and a negative half. So this is a cycle. Okay, if we add these two, we get what? We get 360, right? We get a complete cycle, right? So this one is positive half, then negative half, right? Yes. So positive half, then negative half gives us a cycle. Okay. So that is cycle for you. The next thing we are going to move to is frequency. All right. So it's frequency. Okay. So frequency. Okay, so these are the terms that we are going to use in AC circuit. Frequency. What is frequency? The number of cycles made in 1 second. Okay, so that is frequency. Frequency is what? Is the number of cycles made in what? Made in 1 second. Okay, remember I told you guys that a cycle is made up of a positive and a negative half, right? You can say a complete positive and Yeah, in the negative and a positive half, okay, that is a cycle. So the number of cycle made in 1 second is known as frequency. Then the next term we're going to deal with is period. Okay, is period. Okay, represented by capital letter T. Okay, now period. Okay, period is what? Period is the time it takes to make one complete cycle. Okay, the time it takes to what? The time takes to make one complete cycle is known as period. Okay, whereas frequency is the number of cycle made in what? In 1 second. Okay, yes. So take note, cycle is made up of a positive half and negative half, right? The positive half is usually in positive x-axis, positive y-axis. Negative half is usually what? At the negative half. The negative graph, the negative part, or you can say negative half, is made up is at what? Is at the negative y-axis. Okay, yes. So frequency is number of cycle made in 1 second. Then period is the time it takes to make one complete cycle. Okay, yes. So now if you look at the two formula between frequency and period, you find out that frequency is number of cycle divided by time, right? Yes. If you look at period, is what? Time divided by number of cycle, right? So that's it. That's to tell you that frequency and period, they are what? They are reciprocal to each other. So that is where the formula comes from. F is equals to 1 over what? Period. Okay, you know why? Because period and frequency, they are what? They are reciprocal to each other. Okay, if you look at period, if you look at period is what? T over n. If you look at frequency is what? N over t, right? So they are reciprocal, right? So frequency is equals to 1 over period, or you can say period is equals to 1 over frequency. They are what? They are reciprocal to each other. Okay, so the next term we will make use of in AC circuit is angular frequency, which is also known as angular velocity. Okay, so angular frequency or angular velocity is represented by this symbol here, this letter, which is known as omega. Okay, so angular frequency is equals to what? 2 pi f. Okay, so just take note that this is known as angular frequency, which is also called angular velocity. Okay, so these are the terms we are going to make use of in AC circuit. The first one, we make use of cycle, right? Second one, make use of frequency, make use of period, make use of angular frequency or angular velocity. Just take note of the formula. Angular velocity is equals to 2 pi f, right? Yes. Frequency is equals to what? Number of cycle over time. Then period is equals to what? Time over n, number of cycle. Then just take note that frequency is what? Is reciprocal of what? Reciprocal of period, and vice versa. Period is still reciprocal of what? Frequency, right? Yes. So these are the formulas you need to take note of. Okay, just know them. All right. Now, before then, frequency, the SI unit of frequency is what? Is Hertz. Okay, is Hertz. HERTZ. SI unit of period is seconds. SI unit of angular velocity or angular frequency is rad per second. Okay, so that's all about the terms using AC circuits. Now let's move deeper. Okay, let's move to the interesting part of this class. Okay, so we are done with the introduction, we are done with the terms using AC circuit. Then let's move to the next part, which is the values of current and voltage in AC circuit. Okay, yes, remember, an AC circuit is a circuit with a current or voltage that changes with time, or that varies with time, right? Or that reverses with what? With time. The current changes with time. Okay, yes, the current can moving clockwise can also change moving at clockwise, so it varies or changes with time. Now let's look to the values of current and voltage in AC circuits. Now the first value you need to know, because there are different values of current, unlike in DC. In AC there are different values of current. Okay, now these are the values you need to know in AC circuit. Okay, now one of the values is the peak value. Okay, the peak value. Okay, the peak value. Okay, the peak value. Okay, there are two types. Okay, or should I say okay, oh yeah, the peak value. Okay, inside the peak value we have the peak current. Okay, we have the peak current, then we have what? We have the peak voltage. Okay, yes. So what is the peak value of current and what is the peak value of voltage? It's very easy. Peak value of current is the highest, or you can see the maximum value of current. Okay. Then same thing, peak means highest, right? So peak value of current or peak value of voltage, the highest the maximum value of voltage and current. Okay. So peak current is known as the highest value of current. Then peak voltage is what is the highest value of voltage. Take note, the peak current is represented by this symbol. Okay. Yes, I should I say I sub naught. Okay, or you can also, okay, like by this value. Then peak voltage is presented like this. Okay, V, then put this small thing here. Okay, so yes, so the first value which you need to take note of is what is the peak value. Okay, yes, under the peak value we have the peak current, right? We have the peak voltage. So the peak value is what is the highest value or the maximum value of current and voltage. So take note of these symbols. Okay, so when you see something like this in AC circuits, note that we are talking about peak current and peak voltage. Okay, also peak current and peak voltage can also be represented by something like this. Okay, and okay, to meet maximum. Okay, yeah, so it can also be presented like this, but most times presented like this. Okay, the next value we need to take note of is instantaneous value. Okay, we are done with the peak value, right? Now let's move to the next value of current and voltage. You need to know is the instantaneous value. Okay, yes, so instantaneous value. All right, so now take note, the instantaneous value for current is equals to the peak value sine omega t. Okay, then the instantaneous value for voltage, take note, this is just take note of this formula. Instantaneous value of voltage in AC circuit is V is equals to the peak value of voltage sine omega t. Okay, yes, so take note of it as well. All right, so this is what the peak value is, right? Then if it's something like this one, when you say I is equals to this, the instantaneous value is the instantaneous value of current is equals to the peak value of current sine omega t. Then the instantaneous value of voltage is equals to the peak value of voltage sine omega t. Okay, yes, so what is the instantaneous value of current and voltage? Instantaneous value of current and voltage is that the value of current at any instant of time, okay, or at a particular instant of time. Okay, so that value of current or that value of voltage at a particular instant of time is known as the instantaneous value. Okay, yes, so I is what the instantaneous value of current. Instantaneous value of current is equals to the peak value of current sine omega t, or you can say sine wt. Okay, then the instantaneous value of voltage V is equals to the peak value of voltage sine wt. Remember, W is known as what? Omega, which is the angular frequency or angular velocity. I've given you guys the formula. Is a formula of angular velocity is 2 pi f, right? Yes. So then the next value of current and voltage you need to take note of is the root mean square value. Okay, the root mean square value. Okay, the root mean square value. Okay, so the root mean square value in short form is known as ROMS. Okay, RMS value. Okay, so now, what is root mean square value? Okay, now before then, you know the difference between an alternating current and a direct current. Okay, a direct current, that current is produced by a battery. Okay, flows in one direction, so that's why it's called a direct current. But an alternating current, the reason why it's called alternating current is because it changes with time, it reverses the direction. The direction is not direct. If the current can flows in clockwise direction, it can also flows um, in anti-clockwise direction. Okay, so that current now an alternating current is not produced by battery. That current produced by a generator or produced by a transformer. That current is known as an an alternating current. But the one produced by a battery is known as a direct current. It flows in one direction. Whereas an alternating current flows in different direction. Okay, yes. So it's produced by that current produced by transformer, a generator, those currents is known as an alternating current. Okay. Now, root mean square value of current and voltage. Okay, now what is root mean square, or what is RMS, what is root mean square value of current and voltage, or what is the RMS value of current and voltage? It is that value of current that have the same, it let me write it. So the root mean square value, it is what, it is the value that have the same heating effect, the value that have the same heating effect as a direct current, as a DC. So that value of an AC, of alternating current that have the same heating effect as a DC is known as what? Is known as the RMS value. Okay, yes. Now let me give you guys the formula. So the RMS value of current, we present it like this. The current, then write RO ms. Okay, write RMS. Okay, you might have seen something like this. So the root mean square value of current is equals to the peak current divided by root 2. Okay, yes. Then the RMS value of voltage is equals to what? Is equals to the peak voltage. It's equals to the peak voltage divided by what? Divided by root 2. Okay, yes. Then apart from that one, root 2 we can also, it can, which is something as where root, okay, 1 over root 2 is 0.7071. Okay, so 1 over root 2 equals to 0.7071. Now let me tell you guys something. Now remember, the RMS value of the current is equals to the peak value of current divided by root 2, right? Yes, this thing still something as what? Still something as 1 over root 2 times what? Times the peak current, right? Same goes for here. This still something as what? 1 over root 2 times what? Times the peak voltage, right? Yes. Now in your calculator, just press it in your calculator. 1 over root 2 will give us 0.7071. Okay, 0.7071. Okay, so to give us 0.7071. Now 0.7071 times the peak current will give us what? Will give us 0.7071, then I naught, right? Yes. So times the peak current, right? Yes. Same goes for here. One root 2 is 0.7071. So 0.7071 times the peak voltage will give us 0.7071 V naught. Yes, right? So 0.7071 then V, right? Yes. So just take note that you can use this, okay? So just think that the root mean square value of the current is equals to the peak current divided by what? Root 2. Or you can say root mean square value of the current is equals to 0.7071 the peak current, right? Yes, that's peak current. Or then the root mean square value of the voltage equals to what? The peak voltage divided by root 2. Or you can say 0.7071 the peak voltage. Okay, yes. So just take note that the RMS value of the current is equals to what? The peak current divided by what? Root 2. Then the RMS value of the voltage equals to what? The peak voltage divided by what? Root 2. So take note of those formulas, okay? So these are the important values of current and voltage you need to take note of in AC circuits. Okay. So whenever you see something like this, know that they're talking about the peak current. The peak current is the highest current value of current. Okay, this one peak voltage, the highest value of voltage. Then you see this something like this. You see this one. This is what? This is instantaneous value of current. Okay, which is that value of current at any instant of time. Same goes for the voltage. Okay, yes. Then take note of the formula. Instantaneous current is equals to the peak current sin WT. The same goes for voltage. Then when you see something like this, when you see something like this, IRMS means the root mean square value of the current is equals to the peak current divided by root 2. The root mean square value of the voltage is equals to the peak voltage divided by root 2. So take note of the values. Okay, so we are done with the values of current and voltage in AC circuit. Okay, now the next part we are going to deal with is alternating current through a capacitor, alternating current through a resistor, alternating current through and inductor. Okay, at first let's start with a resistor. Okay, let's start with resistor. Okay, we all know resistor, right? Yes, so resistor is that produce resistance, right? Yes. So what is resistance? Resistance is the opposition flow of current. So resistor is represented by like this, by symbol like this, or you can represent it like this. Okay, so you can represent a resistor like this. Okay, so now an alternating current through a resistor. Okay, now let me draw. Okay, now look at the body. Let me use this diagram. Okay, okay. Now if let me use this diagram. Now, if you see symbol like this, you see symbol like this. When you see something like this in this in AC circuit, know that you're talking about the voltage. Okay, the AC source, the source that produces the alternating current. Okay, so something like this. Okay, yes. Now, AC through a resistor. Okay, look at it. The source produces the current. Current flows through the resistor, right? Yes. So resistor produces the resistance that oppose the current, right? Now, what is resistance? Resistance is what? Resistance is the opposition to flow of current through a conductor, right? Yes. Okay, or you say through or through resistor. Okay, so resistance is the opposition of flow of current. Now, from Ohm's law, we know that volt is equals to I R, right? Yes, so that is it. Just take note of this one, okay? Yes. Then move to an alternating current through a capacitor, an alternating current through an inductor. Okay, so alternating current through a capacitor. Now, what is a capacitor? A capacitor is a device that store charge, right? Yes. Now, then what about an inductor? Okay, so now alternating current through a capacitor and alternating current through an inductor. There is one quantity you need to take note of, which is reactance. Okay, reactance. Okay, now remember the opposition to flow of current by a resistor is known as what? It's known as resistance, right? The operation of flow of current through a resistor is known as what? It's known as resistance. Okay, by resistor is known as resistance, right? Don't worry about reactance. Remember, resistance is represented by arrow, right? Represented by arrow. The SI unit is what? The SI unit of resistance is ohms, right? So, so this is resistance. Okay. Now there's a quantity in AC circuit known as reactance. Okay, reactance. Reactance is represented by the symbol X. Okay. Now there are two types of reactance. We have the inductive reactance. We have the inductive reactance. Then and the capacitive reactance. Okay, so reactance is not found in a DC circuit. Okay, reactance is only found in an AC circuit, whereas resistance is found both in an AC in a DC circuit as well as in an AC circuit. Okay, now reactance represented by what? It's represented by X, right? Now the SI unit of reactance is still ohms. Okay, take note, ohms. Same SI unit as resistance, okay? Yes. Now, reactance, there are two types. We have the inductive reactance and we have what? The capacitive reactance. Okay, now what is reactance? Reactance is the opposition. Remember, resistance is what is the opposition to flow of current. But reactance is the opposition to changes, it's opposition to changes in current and voltage offered by an inductor and a capacitor respectively. Okay, so resistance is opposition to flow of current, whereas reactance is the opposition to changes. Okay, it's the opposition to changes in current or voltage by an inductor or capacitor. Okay, yes. Now, there are two types of reactance. Okay, don't forget to hope you guys know the difference now. Okay, resistance and reactance. This one is the opposition of flow of current to oppose the flow of current, while reactance oppose changes in current and voltage respectively. Okay, now there are two types. We have the inductive reactance and we have the capacitive reactance. Okay, now inductive reactance is represented by represented by X then L. Okay, so yeah, this inductive reactance represented by XL. Okay, then capacitive reactance is represented by what? X then C. Okay, this subscript C is for stand for capacitance, right? Yes. So that's why so if you see something like this, it means capacitive reactance. Okay, then you see this subscript L, it means inductance. Okay, it means what? It means inductance. So when you see this O symbol, X then subscript L, you know that you're talking about, that point is known as inductive reactance. Okay, now what is the difference between these two? Is there's a lot of difference. I give you guys the formula. Let me first differentiate them. Now, inductive reactance is the opposition to changes in current by an inductor. Okay, so inductor, what does inductor do? Inductor oppose, that is on, the current we are talking about here is what is an alternating current. We are not talking about a DC. Okay, so inductive reactance is the opposition to change in current by an inductor. Then capacitive reactance is the opposition to changes in voltage by a capacitor. Okay, so there are two different things. Okay, yes. Now, so in summary, take notes. If you want to take notes, just take notes of this. Okay. So we know that we know that V is equals to I arrow, right? Yes. So arrow is what? Arrow is resistance, right? Yes. Then this is according to Ohm's law. Voltage equals to I arrow, right? Yes. Then that is voltage in a across a resistor is equals to the current flowing through that resistor times the resistance of that resistor, right? Yes. So the voltage, so we can do something like this. You can say so we will need to specify, because in AC circuit there are different voltage. Okay, so we specify V subscript arrow. Okay, so V subscript arrow, that is the voltage across the resistor, is equals to the current flowing through that resistor times the resistance of that resistor. Okay, yes. Same also, we have voltage across an inductor and voltage across a capacitor. Now, before we continue, you see something like this. Know that is a capacitor. Then you see something like this coil, something like this. You see coil like this. Okay, you know that is an inductor. Okay, yes. So yes, you know that it's an inductor. Then you see this one, a capacitor. Okay, yes. All right, now let's continue. Now, VRO, you see that is voltage across a resistor, right? Now, what about voltage across a capacitor? It will be something like this: V then C is equals to the current flowing through that capacitor, then times what? Times capacitive reactance. Okay, then we also have voltage across the inductor, right, which is equals to the current flowing through that inductor times inductive reactance. Okay, yes. So just take note of this. VR is equals to, that is voltage across resistor, is equals to the current times resistance. Then VC, that is voltage across a capacitor, is equals to the current flowing through that capacitor times the reactance, the capacitive reactance. Okay. Then this is voltage across an inductor, is equals to uh, the current flowing through that inductor times what? Times the inductive reactance. Okay. Yes. Now remember, and we all know that yes. Now let's continue. Okay, now let me give you guys the formula of capacitive reactance and inductive reactance. Okay, we all know the formula for resistance, right? So what is formula for resistance? Formula for resistance is what? Voltage over what? Voltage over current, right? Yes. What is the formula for resistance? Okay, yes. Then we can also say formula for capacitive reactance is what? Is the voltage across the capacitor over what? Current. Same goes for this. Okay, yes. But let me give guys the formula of this formula is also correct. Okay, yes. Now what is the actual formula of capacitive reactance? Capacitive reactance is equals to 1 over 1 over omega Okay, 1 divided omega times. Okay, let me use angular frequency. That's the same thing. Okay, so the formula for capacitive reactance is equals to 1 divide angular frequency times capacitance. Okay, then what about formula for inductive reactance? So this is inductive reactance, right? Formula for inductive reactance is equals to what? Is equals to angular velocity times inductance. Okay, so let me come to this place. So, so just take note of that formula, very important. So capacitive reactance is equals to 1 divide angular frequency times capacitance, right? Yes. Now you all know capacitance. Where is the SI unit of capacitance? SI unit of capacitance is farad, right? Yes. So then what about inductive reactance? Inductive reactance is equals to omega times what? Times inductance. Inductance is the SI unit of inductance is area. Okay, yes, is area. Whereas the SI unit of capacitance is farad. What about the SI unit of resistance? Is ohms, right? Yes. So yes. So then what about the SI unit of inductive reactance? Inductive reactance and capacitive reactance. Remember, I told you guys is what is ohms, right? Yes. I told you guys that resistance and reactance they have the same SI unit. They are what ohms. Okay. So this symbol is known as what? Is known as reactance, right? And there are two types of reactance. We have the capacitive reactance and we have the inductive reactance. So reactance is measured in what? Ohms. Resistance is measured in what? In ohms. Okay. Then what about capacitance? I've taught you guys capacitance. Capacitance. Farad. Inductance is measured in Henry. Okay. So yeah, so taking this formula, but we are not done yet. Okay, now let's derive further. Okay, know that capacitive reactance is equals to 1 over what? Omega c. Okay, that is angular frequency times capacitance, right? If we continue, angular frequency is what? 2 pi frequency, 2 pi f, right? I told you guys 2 pi f. Angular frequency is different than angular velocity. Okay, 2 pi f then times what? Capacitance, right? So therefore you can say capacitive reactance is equals to 1 over 2 pi fc. Okay, so if they give you a particular question, they say calculate for the capacitive reactance, they'll give you capacitance, they'll give you frequency. Do it, just do 1 over 2 pi, then fc. Put the formula, put the value of the frequency, put the value of the capacitance, do everything, you get the capacitive reactance. Okay. Yes. Then what about inductive reactance? The formula for inductive reactance. Formula for inductive reactance is what is angular frequency or angular velocity times inductance, right? But we know the angular velocity is what is 2 pi f then times L, right? Yes. So yes. So if they give you the formula, if they give question, they say calculate for inductive reactance. It's very easy. They give frequency, they'll give you inductance. Multiply everything straight. 2 times pi times frequency times the inductance. Okay, so yes. So these are the important formula you need to take note of. Okay, take note of this formula. Okay, so yeah, take note of these formulas. Okay, so capacitive reactance is equals to 1 over angular frequency, angular velocity, or you can say angular frequency times capacitance, right? Yes. If you expand it, you get this. Then inductive reactance is equals to angular frequency times inductance. If you expand angular frequency or angular velocity, you get this. So that is it. Okay, so so yeah, we are done with AC through a capacitor, alternating current through a resistor, alternating current through an inductor. Okay, so we are done with this. Okay, so take note of reactance now, right? Yes, reactance presented by what? Presented by Hex, right? It is the opposition to changes in current and voltage by inductor and what? And capacitor. Now there are two types of reactance. We have inductive reactance and capacitive reactance. Inductive reactance is what is the opposition to changes in current by an inductor, while capacitive reactance is the opposition to changes in voltage by capacitor. Right, I've given you guys the formula. Okay, yes, I gave you guys the formula. I told you guys that reactance and resistance they have the same SI unit, which is ohms. Okay, yes, so yes, yeah. So apart from that, we'll get to this voltage. Okay, we'll get there. All right, now let's move to the next part, which is phasor diagram. Okay, so Let's move to Phasor diagram. Phasor diagram. Okay. Phasor diagram. Phasor diagram. Now let's start with authentic current through a resistor. That is the phasor the phase diagram. Okay. Now this is now we see circuit that contains an AC circuit. How do you know that this is an authentic current circuit? By this source here. Unlike DC, in DC circuits, the voltage source is like this, right? Yes. But how do you know that this is an authentic circuit? It's very easy. By the authentic source. Something if you have something like this, know that this is what this source produces an authentic current. Okay. Yes. So these are authentic circuits. Okay. Now, if you look this circuit, how many elements does this circuit have? You just only have one element, right? Now this circuit that only contain resistor. Now this circuit that contain an AC circuit that contain only a resistor is known as a purely resistive circuit. Okay, a purely resistive circuit. Okay, so that is a purely resistive circuit is that circuit that contains only resistor. Same goes for this. If you see this one, this circuit is a purely what? Is a purely capacitive. A purely capacitive circuit. Okay. Then see this one. This one is a purely inductive. A purely inductive. Okay, a purely inductive circuit, right? Yes. So how is it a purely inductive circuit? Because it contains an inductor. Okay, inductor is the only element in this circuit. Then this one is a purely capacitive circuit because it only contains a capacitor. This one is a purely resistive circuit because it contains only a resistor. Okay. Yes. Now let's focus on this first circuit, this circuit is what is a purely resistive circuit. Okay. Yes. Now take note. In a purely resistive circuit, very important, very important. In a purely resistive circuit, current and voltage are in phase. This is an exam based question. This is like very important. Okay. So in a purely resistive circuit, okay, this is very, very important. Okay. Take note. Take note. In a purely resistive circuit, current and voltage are in phase. Okay, so current and what? And voltage are in what? Are in phase. Okay, that means that their phase difference is what? Zero. Okay, so take note that in a purely resistive circuit, current and voltage are in phase. Okay, so that's saying that their phase angle between them is zero, right? So this is how we represent them. Presented like this. Okay, current and voltage and what? Are in phase. Okay, yes. So, or we can represent something, we can represent it like this. I'm coming. Can represent it like this. Okay, and this one is voltage and this one is current. Okay, yes. So they are the same thing. Okay, so like this, current, then voltage. So they are what? They are in phase. Okay, now look at this graph here. Okay, now look at this first graph. This first graph is a graph of a purely resistive circuit. Why is the graph of purely resistive circuit? Look at it. This graph here, this wave here, this is a I wave. That is the wave of the current. Why this other one is the wave of the voltage, right? Yes. Now if you look at the wave, look at it very well. Find out that both the current and the voltage are in what? They're in phase, right? Yes. I mean, yeah, they're in phase, right? Yes. So there's the phase difference between them is zero, or you can say 360. Okay, so they're in phase. Okay, look at it. The both the crest, both look at the both of the crest. Okay, look at the way the waves are oriented. Okay, so this the current and the voltage they are in phase. Okay, now let's move to a purely capacitive circuit. Once you go further, you now know the difference between these waves. Okay, you know the difference soon. Okay, yes. So we also know that in the current and voltage are in phase, it means that the phase angle between them is what? Is zero. Okay. All right, now let's move to a purely capacitive circuit. A purely capacitive circuit contains only a capacitor, right? Yes. Now take note, in a purely capacitive circuit, use this acronym ICE. Okay, Yes, use this acronym if you know how to forget. I's. It means that in a purely capacitive circuit, I is for what? Current. Okay. EMF. EMF is still something as what? Volt. Right? Still something as voltage, right? So E is for what? Voltage. Okay. Then why this C? Capacitance. Okay. So use this one to remember. In a purely capacitive circuit, current lead the voltage. Okay. Yes. So in a purely capacitive circuit, the current. That's right. Okay. The current lead the voltage. Okay. So let's say that. So yeah, so current leads the voltage, or you can say voltage lag the current. Okay. So what in a so let's say that in a purely capacitive circuit, the current leads the voltage, or the voltage lag the current. Okay. So by an angle of 90 degree. Okay, by what? By an angle of 90 degree. Okay. So currently is the voltage in a capacitive. Use this acronyms to remember. Okay. So in a purely capacitive circuit, current leads the voltage by 90 degree, or you can say the voltage lag behind the current by 90 degree. Okay. So yes, now let me give you now let me yes, now let me show you, let me give you guys the graph. Okay, let me give you guys the graph to understand it further. Okay, so in a purely capacitive circuit, capacitive circuit, remember the current leads the voltage, right? Yes, so the current is usually horizontal. Okay, current is usually horizontal, so this will be current. Okay, then the voltage will go down. Okay, so okay, so yeah, let me do it well. So unlike in a purely resistive circuit, you find out that both the voltage and current are in phase, right? Yes, but in a purely capacitive circuit, the current the current leads what? The voltage, right? The angle of what? 90 degree. Okay, yes. So can the current leads the voltage by 90 degree, or the voltage lag behind the current by what? 90 degree. Okay, now look at these two graphs. Look at these two graphs very well. This is the current, this is the voltage. Now, I told you guys the current is voltage by what? By 90 degree. Now let me show you guys. Now if you look at okay, I can clean okay, where am I to clean now? Let me clean this. Let me clean this pattern. I've used it. Okay. Now let me now if you see this is a wave, right? This is a waveform, right? Yes, this is a waveform, right? Yes. Now this place here, this full place from here to here is what? Is 180 degree. Okay. Then from here to here is under 180 degree. And if we had these two waves together, we get what? A full circle, which is what? 360, right? 180 plus 180 give us 360. Right? Yes. Now if here is 180, that means half of this wave here will be what? Half from here to here, that means from here to here will be what? Will be 90 degree. Then from here to here will still be what? Will still be 90 degree. Right? Same goes for this wave, right? Half is what? Still 90, right? Half 90, right? Yes. So half of this will place 180, this will place 180, right? 180 plus 180 give us 360 degree, right? So half of 180 will give us 90, right? Yes. Now check this wave. Look at this waveform. This is the current, while this is the voltage. Now if you look closely, this full place is what? This full place is 180, right? This full place is 180. Now look at the current. This is the current, this is wave of the current, right? It pass through what? It pass through the center of this 180 of this waveform, right? That center is what? Is 90. Let's say that from the origin to this place here is what? Is 90 degree. Okay. Then from here to here is still 90 degree. Okay. So that's why I tell that. So that's why I tell you that current leads the voltage by 90 degree, or the voltage lag behind the current by what? By 90 degree. Okay. Yes. So when you check these two places, look at this one. Look at this one, this one, this one. Look at it. There's no phase. There's no like the phase angle between them is zero, right? Look at it. Like they are in phase. They are in phase. But if you look at these two waves they are not in phase. They are out of phase by what, by 90 degree. Okay, yes. Then let's move to the next one, which is a purely inductive circuit. What is a purely inductive circuit? A circuit that contains only an inductor. Okay, yes. Now, so this is a purely inductive circuit. This is a purely inductive circuit. Look at the inductor here. Okay, yes. Now, in a purely inductive circuit, I'll give you guys this acronym to remember. Li. Okay, Li. This L is what? Inductance. Okay. So remember, for in a purely capacitive circuit, make use of I's, right? This is current. This is capacitance, right? So remember, this you tell that, this for this, so this capacitance tell that you are dealing with a purely capacitive circuit, right? So that this one is what, EMF, or you can say voltage. They're the same thing, right? Yes. Then this one, Li, this one E is of voltage, I is current. So this one is for what, is for a purely inductive circuit, right? So in a purely inductive circuit, the voltage leads the current. Okay, the voltage leads the current. While this one, in a purely capacitive circuit, the current leads the voltage. Okay, so that is very important. So in a purely inductive circuit, the voltage leads the current by what? By 90 degree, or you can say the current lag behind the voltage by what? By 90 degree. Okay, now look at this third, look at this, look at this graphic, I mean this waveform. Look at it very well. These two places, look at these two places, or this wave is for current, right? This wave is for current, while this one is for voltage. So this two place like this is 180, right? Yes. Then look at the wave of the voltage. Look at the way it is oriented. Now it pass through, look at it, the center of it. Now that's to tell that from here to here will be one to be 90 degree. Then from here to here it's 90 degree, right? Yes. So the voltage leads the current by what? By 90 degree. Okay, or you can say the current lag the voltage by what? The way they are oriented 90 degree, 90 degree. Okay, my wave might not be accurate, but just know that the way they are oriented, they are out of phase by 90 degree. Okay, yeah. So the voltage leads the current by 90 degree. The current leads lag the voltage by 90 degree. Okay, so yes, the voltage lead the current by 90 degree. Okay, they can also in any form. Okay, so that's that in a purely inductive circuit, the voltage leads the current by 90 degree, or you can say the current lag the voltage by 90 degree. Now let me give you guys um the graph. Okay, so if this is for a purely, remember that's the that a purely capacitive circuit is the opposite to purely inductive circuit. In inductive and in capacitive they are opposite, right? In capacitive, current leads the voltage by 90 degree, but in inductive, voltage leads the current by 90 degree. Okay, so now let me give you guys the graph. So like this. So the current is like this. Okay, then the voltage goes up. Okay, so that is difference. Okay, 90 degree. Okay, so that is difference. This is a capacitive. When in the capacitive, the voltage is really down. When in capacitive, when in inductive, in a purely inductive circuit, the voltage is really what? Really up. Okay, so 90 degree, 90 degree. Okay. Okay, yeah. So that's all about the phasor diagram in AC circuit. Okay, and let me say next part,